Hello, my name is Marcus Nordenstam. I am a product manager at Autodesk, focusing on Bifrost. With the release of Bifrost version 2100, many new long-awaited capabilities will arrive, including spatial queries and ease of use improvements, a new point scope, and things like that. So I wanted to demonstrate a lot of these features kind of in context, while at the same time demonstrating something that you might actually want to do in a real production. So with that in mind, I've created this tutorial to show how to create a reusable disintegration effect that will work on production assets that have animation and deformation applied to them, that even have UVs and textures, maybe displacements. To really kind of take all these new features through their paces and apply them on some kind of, real world scenario. So the other thing too is that the setup I've created here does even provide some artistic controls, like the spread speed and the fracture width and the disintegration rate, things like that. So with that, I'll show you, how to create this whole effect from scratch. I'll show you how to build the graph and everything using only the nodes that are included with the Bifrost 2100 or later versions, and the certain compounds from the Rebel pack. So let's get started. So here we have the effect and the graph and everything in Maya here. So here's our face. The face is textured just to show that the UV coordinates would work. So if you did have a real texture or displacement map or something, then the idea is that this setup will still work. So there's a couple of different layers to this effect. So the first layer is just the disintegration of the mesh itself. So if we zoom in, we can see how the mesh is actually breaking up according to some kind of pattern here. You can kind of see the cracks forming and breaking up the mesh, and the parts of the mesh are also disappearing. There's another kind of section to the effect or layer, which is the dust particles. So if we take a look at that quickly, you can see here, it's a little hard to see because the shading is bad here, but you can see the outline of the particles as they are starting to kind of spread and break up as well and disappear. Now, the way that all this works is that basically we're growing an attribute across, or property, a point property across the face with the mesh. And we can take a look at that too. We can visualize that. So if we do that, we can take a look here and see here, we can see these points that are kind of spread across the face mesh. And we can see here how this property is kind of growing across in kind of a fracture-like pattern. And that's really driving the emission of these dust particles, and it's also driving the breakup of the actual mesh geometry. And then finally the other kind of layer part of this is this velocity field we're generating that is controlling the motion of both the faces that are being broken up of the mesh, but also of the particles. So it's basically, the main thing is essentially to be able to break up a mesh and to be able to spread or grow this property that's called point age across in a certain way with artistic controls, and then being able to disintegrate the mesh from that and be able to generate dust particles from that, and also being able to generate a velocity field that controls that. So those kind of are the different layers of our effect. So in the rest of the video, we're going to go through each layer kind of in the order they are used. So we'll start with the ability to take a mesh and turn it into a disjoint set of faces so that you can actually break up a mesh. And while doing that, keeping UV coordinates and everything else intact, making sure that it also works under deformation or under animation. And then we'll take a look at the kind of heart of the system, which is this point face age growing compound that actually creates this growth pattern of a property that we can use to control and drive the effect. And then the other parts are fairly straightforward: the actual disintegration and the particle and the velocity field generation. So let's get to the first one. All right, so in this first part of the tutorial, what we'll be doing is basically just getting to this point. We just want to set it up so that we can take a piece of geometry, a sphere, a good one, and just blow it up. This is the beginning of our effect. We need to be able to detach basically faces of a mesh so that we can then drive them around. We can see here how we're going to do it. We're going to do it with particles or points really. So you can see the points here, and if you take a look, you'll see that the points are in the centers of the faces. And so we're basically doing a detach thing. We're detaching the faces from the mesh. We're simming the midpoints of those faces, and then we're driving the mesh face positions from those points. And this is just a point scope that I'm using to look at the points. So let's get to it. Okay, so in this first part, we're gonna build a compound that will detach all the faces of a mesh and create a new mesh where each face is disjoint from the other. This is necessary in order to make our mesh explode or, fall apart the way we want it to. So we're going to start from scratch. We're going to create the graph. So by the way, of course, once you've created this compound, or if we make compounds like this part of our standard library, or perhaps the community will make one and share it, or whatever, obviously you don't need to be doing low-level technical visual programming like this every time you want to disjoint a mesh. Again, the whole point of Bifrost is that it does give you the low-level power to create these kinds of advanced types of geometric topology-based compounds, but we're not suggesting that you need to do this kind of visual programming every time from scratch. So this is both kind of a tutorial on visual programming with geometry, as much as it is providing a useful building block for you to go forward with. So with all that said, let's do it from scratch. So got a sphere right here in Maya. You obviously bring in my geometry into Bifrost by middle mouse clicking, dragging, and dropping in. So drag and drop. And we're going to make our compound here, make an empty compound. And let's call it make disjoint mesh. All right, so here's our regular mesh coming in. So the first thing we need to do is get our structure. So this is now getting fairly technical. We're diving right into the open data model of our geometry model in Bifrost. As you can see, we get buffers and arrays of data. Everything in a mesh in Bifrost is a series of arrays of data. So you have a buffer or an array of float threes for point positions. You've got an array for face offsets, which is basically every element in this array gives you the index into the face vertex buffer for the first vertex of each face. So element 20, for example, in the face offset would correspond to face number 20 in your mesh, and specifically the first vertex index in that face. So what we really want to do is basically get run through this thing and get slices of the vertex index array, where each slice, so each group of face vertices represent the indices for the vertices for each face. And so what we basically want to do is just duplicate all those and create a new mesh where we've duplicated all the face vertices into a new mesh that we can then work with without affecting shared vertices or anything like that. So there's a bunch of ways to iterate and do all this kind of stuff. To be efficient, I'm going to use for each, because for each runs in parallel. And what we're going to do is say, well, let's run through all the faces. So the first thing we're going to do is say max iterations will be the face count. That means for each will run all the way up to the face count. And then we're going to plug in the face vertex. Actually, we're going to plug these in order. So point position, face vertex, and face offset are all going to go in here. Then what we do in here is we're going to just get that slice per face. So so this will be, we'll first use the axis offset array compound to get the offset array with the current index, and then get the array slice from there. So start goes to start, end goes to stop, and the array we're slicing is the face vertex array, which is the indices for each face. And that's it. So we now have, this is going to be in a small array of some number of vertex indices that correspond to each face we're traversing across. So So if you want to get the vertex positions, we just simply get from array. So the indices for the face positions will be given here in the slice, and the point position is the point position. So here we go. So now we are basically getting a slice of point positions here for each face. And that's what we're interested in outputting, so we output that. We also want to get the number of vertices per face, which we can simply do by doing a array size. So get the size of the array, I'll just get it here. So basically how many vertices are in each slice, i.e. how many vertices are in each face. And I'm going to go ahead and turn this into an unsigned int, because we're going to use this later, and we're going to want that to be unsigned int and not type long like it comes out there. All right, great. So that's basically it. Now, coming out of here, what happens is that this is obviously iterating across every single face. And note that, oh, by the way, I need to rename. This should be, let's call it disjoint point position, and this is verts per face. So that's, or I should call that vert count, maybe. So this is the number of vertices per face, and these are the actual point positions per face, which are disjoint because they're not shared among faces anymore. So anyway, so obviously what's happening here is that we're getting a little array. And by the way, you can always know it's an array in Bifrost if you see this. If you see the port turn into like hat-looking things, looks like a hat. That always means array. So you can see here these are squares, so that's single values. But that guy right there looks like a hat, so that's an array. So we can see here that you know, we're getting a slice, so an array of positions and an array of actually not an array here, but you're getting an array of positions out of here. So that basically means that per face I'm getting an array of positions. So that then means that we have an array, right? So the first level of the array is the array of faces, and the second level is the vertices, the array of vertices per face. So we can flatten that out. So we're going to do flatten nested array, and that will then take that array of arrays and turn it into a single array, and that's what we want, because we want to have a single array for all of our vertex positions for our new disjoint mesh. And with this guy, and so where all this is leading is that we eventually want to construct a brand new mesh using construct mesh. So here we're going to be able to create our new mesh, which is our disjoint mesh. And we're done with the first step of it. We can just plug in point position, and that's, you know, we're done. We also need to reconstruct a new face offset and a new face vertex array. So the face offsets is just going to again be which index into the face vertices array we need to jump to for each face to start reading the right vertex connectivity information. So that just happens to basically be this array here, because well, so every element of this array here we created is the number of vertices for that face. So that actually means that if we take the cumulative if I can type, cumulative sum of that, that's going to produce a new array in which every element is the sum of all the previous elements, which is exactly what we want for the face offsets. The only problem is that the first element of this is not going to be 0, because the first element will actually be the vertex count for the first face. So we do want that first element to be 0, because we want the first face to start indexing from 0. So I'm just going to put down the value node and make it a unsigned integer, because that's what that type needs to be. And then I'm just going to do a build array manually here. So there's many ways to do this, but this is the simplest way, I think. So we just start our array with 0, index 0, and then we plug in this cumulative array, and that gives us the right indexing for the face offsets. And then finally, for the face vertices, it's very simple. Obviously, we're just counting from 0 all the way up to the number of vertices and you know, so basically it's like if this was phase, the first phase, it would just be 0, 1, 2, 3. Say this is the second phase, it would be then 4, 5, 6, 7, and on we go. So we're just going to create a sequence array for this. And the size of it will basically be the very last element of the cumulative sum array. So take last in array, that's the number of vertices, or number of indices, and then the start. Well, let's do this. Let's set the value type to be an unsigned int. Unsigned int, and we're stepping by 1, and that's the number. So that's it. That will create an array, and we'll just plug that right in. And that is basically it. I'm going to plug that back out. Call this Disjoint Mesh. And let's hide our original sphere and go ahead and plug that in, and look at that, we got a mesh. So let's now go ahead and check if you know, it actually is disjoint, right? So in theory, if we start displacing the vertices of this new disjointed mesh, then we should start seeing separation happen. We should start seeing these faces actually separate from each other. So let's do that. So we'll get point positions and use noise. We'll use curl noise here just for simplicity, and use that noise vector to displace each vertex. Now, because all the vertices are bunched up in the same place, they're all going to get the same displacement vector for every corner of the face. So that's actually not going to tell us, we're not going to see face separation because all the vertices are going to move the same way. So let's use the indices of the position array and feed that to the seed of the curl noise. That way we'll ensure we get unique vectors per vertex. So we'll let's see here, get array indices. So let's just get the array here, and this is not special to point position. This will work on any array, but using it here. And then we'll just add that displacement vector, which is now going to be unique per index of the position, to the position. And then we're going to set, and then we're going to set point position back to the yeah, so our mesh now will have the updated positions, and let's take a look at that. Oh yeah, look at that. So clearly they are disjoint, I think. They're a bit crazy and wild, so how about we just fix that. So what we're going to do is just scale down that displacement a little bit. We're going to make a value node, make it 0.1. So let's scale down that displacement by 0.1. Throw in a multiply. So let's take that noise vector we're getting here and scale that thing down by 0.1. And yeah, look at that. So we're in business. Also, I accidentally hit a key here under options. So I think I accidentally did show node types. That's why we were getting, if you toggle it on and off, you can see, if you show node types, you can see that's a compound as an input, and it like colors the nodes and stuff. So it's kind of helpful, but I usually just work with it turned off. So the next step here is to also make sure that this will work with UV coordinates. So while we're still working on this, making our disjoint mesh, let's just upgrade it a little bit, make sure we have UV coordinate support. Right now we don't, because we're only carrying over the positional information and no UVs. So I think the easiest way to kind of go about this is to start off with going back to our Maya sphere. I'm going to hide the Bif shape. And let's just first of all make sure that we have UVs on this thing. So I'm going to go and just assign like spherical UVs. Done. And then we're going to put on a material. I think I have a standard surface here. Make sure we're hardware texturing, and let's also display the material assignment, and go here, and then we'll go ahead and add like a checkerboard pattern or something simple to the color. So we have UVs, and it has a material with a texture on it, so that's good. And then now if I hide that and I unhide the Bifrost, we can see that our disjoint Bifrost mesh has lost, well actually it doesn't have the right, so if I first assign the material, so standard surface 1, we can see that we now have the same material, but whereas this one has UVs, so we see the texture, whereas we're missing UVs here, so we don't see the texture. So to do this, so in the future, I'd expect us to add UV information to this get mesh structure, probably, or certainly, make it more useful in that sense. But at the moment, we don't. So we're going to actually have to import this guy. So I'm going to import this compound by making it editable. So we're going to actually go in here and upgrade it to actually also provide us with the UV information. So that's not too hard. We're just going to find a good place to do that right here. All right, so what we're really going to try to do here is get two pieces of data across here, the actual UV coordinates themselves and the UV indices. So the one way to, also in general is useful if you're trying to understand how properties work and what they're called and their types and things like that. You can literally just put a watch point on any connection in Bifrost and take a look. And so in this case, since we already applied UV coordinates to the mesh in Maya, when it comes through into Bifrost, it will carry over that UV information, although it gets renamed and represented in the Bifrost way inside of Bifrost. So they may not have the exact same names that you would expect in Maya. And we can do other videos on all that kind of stuff. But for today, I'll just mention that what the coordinates or the properties that we're looking for is the face vertex UV, which are the actual, it's a float 2, so the actual UV coordinates of the actual UVs, and the face face vertex UV index. And this is similar to the face vertex, which is the connectivity of the actual point positions for the vertices. This is the connectivity of the indices of the UV coordinates and not the positional coordinates. So these are the two guys we want to bring over, and we want to do the same thing to them as we did to the positions. So with that said, we're going to dive back in here, and the easiest thing is just to take a look at how we deal with these other guys. So the face vertices, I'm just going to copy and paste this. And so the one difference here is that the way that the face, so this is face vertex UV, is it? Let me check. Actually, let me open up that watch point again. I forgot the name of it. It's face vertex UV and face vertex UV index. That's right. So go back in here. So what we're trying to get is the face vertex UV index. So those are the indices, and that particular property I happen to know is a little bit encoded slightly differently under the hood. So we're actually going to have to make this editable as well, and go in here and do this one little. It's not a hack, but it's just we just have to take care of this. So the property we're trying to get here is not called data; it's called indices. And so again, this is a kind of a low-level thing. I think we'll probably need to update our structure node to include this stuff, so people don't have to do this in the future. But for right now, this is the way to do it. So this will now give us the actual face vertex UV index UV connectivity. So let's get that, and we can call that for what it is. It's the face vertex UV index. And then we want to also get the actual buffer. So instead of point position, I'm just going to do a get geo property node here and connect it to the mesh here. And these are, we happen to know, well, we saw that before, it was float 2 because it's UV coordinates, or 2D coordinates, so float 2. And that would be face vertex UV. And we hook that up. We'll call it, just for usability, readability, face vertex UV. And that's it. So we now have access to the UV coordinates. So now we're just going to bring these guys over to our for loop here. So this is the thing that's iterating over every face. So we can now pick up the UVs per face as well. So I'm just going to do another get, actually another slice array. So we're going to slice, so we want to make a slice now in the, instead of slicing face vertex, we're going to be slicing the face vertex UV index. So that's what we're slicing. And then we're going to do a get from array from that, using that slice. So those indices in that slice that are now UV indices, let's read the actual UV coordinates from those indices per face. If I could click, it'd be great. Great. So, and that's it. This will then give us our, so this is disjoint face vertex UV. And of course we'll have to flatten this too, because this, like the positions, is an array of an array. So let's do that, nested array, and we'll put that in the, we'll just go ahead and do a set geoproperty and hook that up there. And we know this is called face vertex UV. Whoops. UV. So now we're gonna go ahead and hook that up, and that, look at that, we got UVs. So note that I'm only actually getting, I'm only setting the face vertex UV property here. I'm not actually setting and reconstructing the face vertex UV index. And that's just because I happen to know I don't really need to do indexed UVs in this mesh, because of the fact that every single face basically is completely independent from all the other faces. In that scenario, indexing the UVs is less important, and it's also a little bit quick and easy for me to do it this way. We can certainly get more fancy and do it and set up the indexing and everything too, but for these purposes, I think this is sufficient. So that takes care of the UVs. All right, so the next step is to make these faces that I've now detached from the mesh, to make them float around freely. Really driven by a particle system would be the best, and so let's set that up. So the two things we need to do that is, one, some kind of points or particle system that will move around, and then the second thing we need to do is make sure that our faces can be driven by those particles. So there's a bunch of ways to do this kind of stuff, but the simplest one that we'll go with here today, and that I would recommend, at least for Bifrost 2100, is it's just to store, so basically compute the face point, the midpoints for each face, and then store the relative offsets to each vertex per face to the corresponding face point. That way, when the face point moves, we can then reconstruct that face around that face point by just simply adding back the face points coordinates to each relative vertex coordinate of the face. So that's what we're going to do. So that basically means we build a new point object or point cloud from the face points, and so that means that, and then also we need to store relative vertices. So let's just do that all inside of make disjoint mesh. So first part is we go inside this for each loop here, where we're constructing all that disjointed mesh data, and that's the right place to also figure out where the center points are. We're just going to compute center points by taking the average position of all 4 vertices per face. So let's do sum array. So we'll sum the array of vertices here, and then we're just going to divide that by the number of vertices. So the sum of the vertex coordinates divided by the number of vertices which we are computing here. See, vertex count per face. So that gives us the face point. So I'm going to call that face point position. And then we also want to store and compute the relative. So we basically want to transform our vertex positions here per face to be relative coordinates, relative to this point, to the face point. So that's very simple. We simply subtract away that from the coordinates. So take the original vertex coordinates and subtract away, oops, that newly calculated vertex position, and that gives us relative coordinates. So I'm going to call that point position relative. That's it. So we have our face points here coming out, and then we have the point position relative, the relative positions, which again is an array of an array, because just like the disjoint point positions, we have an array first for every face, and then within that array, a sub-array for the list of the little vertices for that one face. So because of that, we need to flatten. So we're going to flatten that relative array into a single array, and then we're going to store that flattened array as another kind of user property here. So it said geo properties. So geo properties are basically custom user properties. Well, they can be official ones too. It doesn't really matter, but we use them here to set our kind of custom data. Whoops. Yeah, there we go. So we're going to call this point position relative, and hook that up. And so then the other thing we need to do is generate a point cloud from all those face point positions per face. We're just going to output them directly all the way out here. So because we're not going to bake that data into the actual mesh, we're going to make a separate point cloud out of that. I could of course make the point cloud in here, but I'm going to do it outside. One other thing we can do as well here is we can take a look just at this disjoint mesh data structure flowing out of here, put a watch point, and we can also now see that we have our, we have our UVs and everything, but we got our point position relatives that we added as well. So that's all good. So finally we want to make a point cloud, so I'm just going to do construct points and use those face point positions and take a look at that. So I'm just going to make a separate output now for this guy and just take a peek. So look at that, we can see little points, and if I hide the mesh, whoa, that's barely visible. But hey, we got a point scope, so let's put up a point scope. So let's see, let's do this. There we go, much easier to see that. So I'm just going to use this output for now. All right, so we have our points for the point cloud to now drive our faces from the mesh. And we also, of course, need to build a particle system of some sort to push them around. But before we do that, I think the smartest thing is to go ahead and make sure we can, in fact, drive our faces with the points. So as we just did, we created this relative vertex position, so-called point position relative, that are relative to the face points. So let's go ahead and use that now to create a little compound that will drive the mesh faces from the points and get that set up, and then we'll simulate the particles and watch our faces go flying. So without further ado, let's get to it. So I'm going to put down a compound, a new one, and we'll call this drive mesh faces with points. And of course the points we're driving with will be these face points that we're looking at here. So first things to do is to get the mesh. Let's drive that mesh and let's get these points in there. So we got our mesh and we got the points. And ultimately what we're doing is we're just setting new point positions on this mesh. So again, let's start with that get mesh structure to get some of the stuff we need to run through our faces of the original mesh. And we got the points, so let's do that. We also want to get the point positions of the actual points that we're driving with. Now, of course, as you recall, the relative vertex positions, which are the ones that we need to be dealing with here, are not represented here in our standard mesh structure, because that was kind of like a user added property. So we can use get geo property to access that user added property. So let's get that. And the value type here will be, it's a matplotlib3 because there is a vector 3 for positions. And they are called point position relative. Great, so we got the mesh structure, we got our relative point positions, and we got the positions of our particles, or phase points. And then similarly as before, we're just going to do a parallel for each to be efficient. We're going to go through every phase of that original mesh. We're going to get the phase vertices and the offsets so that we can get the slices for every phase, little set of vertices for each phase. But now we're not going to get the point position, we're going to get that relative point position, because that's what we want to be using. Point position relative. By the way, the names of these inputs and outputs don't matter, like in terms of how the system works. I just like to name things to make it clear, to make it easy to read. That's all. And that's the point position of the particles. All right. So yeah, of course, if we want to now translate our relative phase positions to the world space phase positions and have that particle drive it, it just is quite simple. All we need to do is add the relative vertex positions to the position of the particle that is driving that entire phase. So we'll, as before, we're going to start by accessing an offset, the offset array from the current index. The current index is the current phase in the loop, and then get a slice out the indices for that current phase, slice that out of the index array, which is phase vertex, and then as before we get from array to get the indices, to get the actual vertices, the relative vertices positions. So there we are, and then we, as I said, we simply just want to add to that relative vertex positions, we want to add our particle's point position. But here is where it's easy to make a mistake. If I just connect this, what I'm actually doing is I'm attempting to add the entire array of point positions for all of the particles to the 4 or 3 or however many of the vertices we have for the current phase. So let's say that we have a quad phase, so it has 4 vertices. So then that means the 4 vertices of our current quad phase is going to try to be added to all of the particle point positions here. What will happen then will be that Bifrost will look at that and say, hey, I'm trying to add 2 different arrays of different sizes. So I'm just going to clamp to the smallest size and only add only do the addition for that small amount, the smaller array, which would be 4 if it's a quad phase. And that means I only get 4 vertices coming out, and it's only going to pick the first 4 particle positions here. Anyway, that's all nonsense. This is not what we want. What we actually want is for every iteration in this for each loop to only pick up a single point position for the particle corresponding to the entire phase, right? So the way to do that is just to set the iteration target to be true. This basically means that when, and I could set any of these to be iteration target, by the way, but if you have an array input to for each loop, and this also works the same on iterate and do while, the other looping constructs in Bifrost, but in this case, if you set an array input to be an iteration target, it just means that that for every iteration, the system is automatically going to pick basically the current index value out of that array and expose it as a single value. So that means that now we're just adding a single value for all of the 4 vertices in each phase, and that's what we want, right? Because for every phase, we just want to pick that one vertex that corresponds to all 4 phase vertices and add its coordinate to all 4 of them. So that's why we do that. I should also mention this is equivalent. I could have said, hey, let's not make that the iteration target. I could have just done get from array like this, right? It would be the same thing. So if I take that array and I say I'm going to use the current index in that array and feed that to this. So that would be the same thing. This is exactly the same thing. But the shorthand for doing that inside of loops, so you don't have to do an extra get from array, is just to set the iteration target to be true, and that does that for you, and then you can just hook it up. So anyway, with all that said, as you can see, we didn't really have to do that much. We really just get a slice from the face vertex indices and then look up those indices from the relative positions, and that gives us the relative 4 or 3 vertices, depending on if it's a triangle or a quad face, and then we add to that our current point position to all 4 of them, and that brings us back to world space, and that effectively translates the face depending on where that point or particle has moved. So now we're getting the world space positions out, and of course, since we're doing this per face, the output again is a double array. It's for every face, and then for every face, the internal array, it represents the newly displaced vertices for each face. So we need to do the nested array again to flatten this from our Rebel pack, by the way. So you see the compounds with the R refer to the Rebel pack compounds. So you do need to get the Rebel pack installed, which you can download the same place as you would download Bifrost. All right, so that's it. Now we just need to set point position. So these are now the displaced vertex locations in world space for each face, and we're going to set that back on our disjoint mesh. So basically, I'm just going to move all this down a little bit. There we go. So essentially all we're really doing is taking our disjoint mesh and updating the point positions on it, and we do that by iterating through all the faces and doing all this fancy stuff. And that's it. They are now there. So we now have our compound working, I think. Let's test it. So this is supposed to drive the mesh with the points. Now, we already had that little displacement we did earlier, where we added the curl noise and everything. So why don't we just do this? We can, so instead of doing that directly to the face vertices as we did before, we now can simplify all this. First of all, we don't need this get array indices and driving the seed anymore, because now we're doing curl noise on the face points, and the face points are uniquely located in space per face, so that will work. So what we do is we get our points, we're going to use those points. So now we're getting the positions for our face points, we're looking up the curl noise for them, and then we're scaling it down a bit and then updating. And then basically this is like a simple, almost like a simple simulation step where we update the positions of those face points according to curl noise, and we set them back. So we want to be setting them on the construct points here. So here we go. So this is like a kind of like a small simulation step without a loop in it right here. At the end of the day, anyway, the positions are going to be updated, so we can check that here. I'm going to move all this stuff over a little bit. It's a bit of a mess right now, but we'll clean it later. All right, so now keep your eyes on this viewport here. We should see them move. There, see they moved? In fact, we can get rid of that scale down. Maybe it's fine just to go full hog and move them a lot. There we go. They are clearly moved. So we have just moved our face points according to some curl noise. That's what we wanted to do. So let's get rid of this. All right, let me just clean this up for a second. It's a bit messy and it's hard to read it. So let's see here. Okay. So get point position, get the curl noise of it, add. So basically update our face points via this curl noise displacement. And that's just the point scope to see this thing. And that's it. All right, great. So, so the simple way now to check if this compound we made works is to plug in the displaced point positions now here into the points, and then hook up this to the output to see the mesh. And let's see, turn on the display. Yeah, look at that. Look at that. So we can see that we detached. So basically, yeah, we detached our our sphere using our homegrown, making a disjoint mesh. We pulled out the face positions that we create a point cloud from, and then we offset that point cloud. And now we plug that point cloud into that disjoint mesh to actually drive the new position of every face in the mesh completely independently. And not only that, but the UV coordinates should be intact. And they are, except that we forgot to, I started a new scene here, so I actually turned off the materials. So let me correct that, and we can see that our material should still be okay. So let's see, material attributes, assign existing. Yep, and we can now, if I hide those points, we can see that there is a texture map there. So all that stuff is still working. So yeah, that is it. So the only thing remaining now to really get to the end of this first section is to turn this whole thing here, which is right now just a simple step along noise vectors or a noise field kind of, to turn this into an actual simple particle simulation that moves the particles around. So we'll do that next, and then we will have achieved the first part of our effect. All right, so let's build a custom particle solver for simple particle motion here. So I'm just going to make a compound. This will be kind of our core compound for our particle solver. So the way simple ones work is that you literally just have motion vectors, and then you update the position of the points according to some motion vector. And typically that motion vector would be a velocity. So you would typically integrate that with time, so that the length of your time step in the timeline multiplied by that velocity would be your update. And so that kind of thing is called an Euler integration or forward Euler. So I'll call it forward Euler step. And so basically what you do is you multiply so two values, which is going to be the velocity and your and some kind of scale on that velocity. Actually, the scale we already know is going to be time. It's going to be the frame length. So we can just do that. Oops. And we know velocity is a it's going to be a float 3. However, I think yeah, that's fine. So we'll let that be a float 3, and this is actually our position. So we're going to make that a float 3 as well. And we're going to update our position using that new bit of velocity there, and that's it. So what comes out of here is out position. So this is our little guy to do the update. Let's hook up the point position to the position input here, and the velocity we're just going to say it's going to be the curl noise, and then the new position is what we set here. Get rid of this, and there we go. And we can see that immediately that worked, except it looks like it doesn't, but it did. It's just very subtle. We just need to make a stronger, like a more amplified curl noise effect. So I can put down a value here and say, hey, let's do 10 times stronger. We can do that. So multiply our noise by, say, 10. And we'll get a stronger offset like that. And that's fine. So the next step is, hey, we actually want to simulate, we want to keep state. So every frame, from frame to frame, we want these positions to be remembered, so that if I hit play, it's going to keep offsetting positions and not start do them from scratch. So the way to do that is you have to create state, and the way we do state in the graph is through something called feedback ports. And it's also pretty straightforward. So now the first thing about feedback ports, which is how we keep state, is that they can only be set as pairs of ports on a compound. So as soon as you get into this, the first thing you need to do is create a compound, because if you don't, then you can't really set feedback ports on anything. So we'll make a compound. I'm going to call this simple sim. And then what we're going to do is, actually, you know what? It's a simpler way to do this, because we're basically doing what's in here. I'm just going to do this. I'm just going to I'm going to select our little set of operations here and do Control G to group, which is also the shortcut for creating a compound out of a selected set of nodes in Bifrost. And this also simplifies our top graph quite a bit. And now this whole thing is what I'm going to call simple sim, or I'll call it sim face points, because that's really what we're doing. All right, and so here we are inside this thing. I'm going to make this bigger. Okay, so start forward all there. Right, so here's the thing. So on the very first frame, so whenever you have a sim, you always have to define a start frame, because you need to know what frame you're like starting everything on. So what I'm going to do is put down a time. Actually, we already have a time node here. No, time node is in there. And I'll put down a time node here. And then I'm just going to check. So equal if. So let's do this. So we'll say if the frame, if the frame is equal to another frame, which is going to be what we call our start frame. So start frame. So basically we're going to say, you know, if, so basically if the current frame is equal to the start frame, if that's true, we know we want to construct our points and initialize everything. And if it's false, we know we want to be running the sim and getting the state from the previous frame. So a clever and a nice way to do this is to make another compound out of this called a switch. I'm going to call this switch on frame, on start frame. And if we go inside there, what we're going to do is basically just plug these guys true and false through, and I'll call this on start frame and on, I'll call it sim frame, meaning frames that are not the start frame, therefore we're simulating. All right, and these are auto ports. As you can tell, we haven't explicitly set their type yet. By default, Bifrost will infer the type to always be a float if you don't set it explicitly. Or if you don't connect something to it. And you know auto ports because they have those little bars in front of them. So they're kind of able to adapt to whatever you do to them. But what we actually want to do here is say that we have this geometry coming in. So we're going to say on the start frame, you know, get this geometry, and this geometry, of course, is our points. So maybe we should just call it initial. So initial points. These are the points that we construct. So on the start frame, let's get those initial points. But on the other frame after that, I'm actually going to pull on a new thing here, and I'm just going to call these the sim points. And then that's what we're actually feeding to everything else here down the road. So that's basically it. We're switching on the start frame. On the first frame, we're getting the initial points, and every subsequent frame after that, we're pulling from the sim points. The way to set up the state is that we have this out geometry. Let's rename that to out sim points. So basically, what's going on here is what we want to do is create a feedback between the out sim points and the sim points here, so that after the first frame, the data here sits here, but then the next frame, when the next frame is computed, it can send that data back to the sim points here, and so then, you know, it propagates the last frame's data through the whole thing again. So the way we do that is we either go to the end, I typically just take the output, but you could also go here to the input and do it, but I'll go to the output port and say set port feedback, and here I get choices. These are all the different input ports that I could pair it to, that I want the feedback to go to at the end of the frame. So of course I don't want these. What I want to send the data to the sim points port. And you can see now that this guy turned red, and that's because they can't be auto. You see this guy's auto here, it's got the bar. So I need to go and explicitly set his type to be a type of object, because all these blue, there's object right there, and that fixes it. And the reason why this is important is because for feedback ports, they have to be strictly typed. They can't just be inferring things. Those are the rules currently. So let's read this now. Let's see if this makes sense to us. We're basically saying that, on the first frame, grab those initial points and get their position, update them using curl noise, and set their new positions, and then send them out to be drawn. And that's fine. But then the next frame, because you can see the feedback icon on here, it's going to go back to the port that also has the feedback icon, and so the next frame we're going to say, hey, we're not on the start frame, we're on a sim frame, so pull from here, which is the feedback port, which contains the data from the last frame. And now we're going to get the last frame's positions, update them, and then store and feedback and so on. And that's how you actually get the particles to move. So that's that, and that should be our simple, that's like a super simple solver we just made. Now, start frame has to be 1. Ta-da, that's the start frame, because it was 0 by default and there was no such frame. So let's see, I'm going to press play. Look at that. I'm going to back up a bit. Well, it seems to work. And that's actually it. This is the end of our first part of our first section here. Being able to break up any mesh from Maya, carry over the UV coordinates and deal with all that stuff. Roll our own simple particle solver, very, very simple, to drive the midpoints from the meshes, and then roll our own simple compound that will actually allow points or particles that we're simulating to drive the actual positions of faces. That's great. This is actually a big part of our effect, so well done. Now we're going to start looking at growing that property to control when the face starts breaking, when the mesh face begins to break up. Because right now we're just breaking up the whole mesh with no caring about any kind of a pattern or anything like that. So as you can see here, we're just all the faces get hit at once. So that's coming up next.